In this next section, we'll be going over three of Euler's theorems for circuits. Alright, the first one is Euler's circuits theorem. If a graph is connected and every vertex is even, then it has an Euler circuit. At least one, sometimes or usually more. If a graph has any odd vertices, then it does not have an Euler circuit. There's no way we can end at the same place we started while hitting every edge only once. If there's just one odd vertex, it's going to mess it up completely. Here's some examples below. Graph A, of course, does not have the Euler circuit because it's disconnected, so we can move on from that one. Graph B has some odd vertices. If you notice, looking at graph B, vertex C and vertex E are odd, so that kind of counts that one out, as well as B is also odd, so that doesn't really work. And then in graph C, everything's a little bit different. We have a couple lines added there. All the vertices are connected and they are even, so there is some kind of Euler circuit, and I'm actually going to show you that one here. So if we just start at any of them, really, I think it should work. We could start at F. We'll just go around the perimeter here. All right. Okay, so done pretty easily. We finish back at F. Alright, now we have Euler's path theorem. So it's kind of similar, except we're not going to end up in the same place. So if a graph is connected and has exactly two odd vertices, then it has an Euler path. And so at least one of those paths, sometimes more. And it must be exactly two odd vertices. If it has more than two, it will not have a path. So looking at example A again, we still have the disconnected graph, so we know that's not going to work. Looking at example B, let's highlight some things here. So we have C, there's an odd vertice. We have G, E, and B with 5 edges coming out of it. So that's 4 odd vertices. That's too much, so there's not going to be a path possible for that example. Let's look over at C. With example C, there are no vertices that are odd. And in this case, we actually can't have a path. For a path to exist, there has to be exactly 2 odd vertices. There are circuits in this problem, but no paths. So nowhere in this chapter are you going to have them both occur. Either it has an Euler path, either it has an Euler circuit, or it has neither. Alright, the third theorem is Euler's sum of degrees theorem. The sum of the degrees of all the vertices of a graph equals twice the number of edges, and therefore is an even number. And a graph always has an even number of odd vertices. So let's just look at graph B for this. Ignore A and C for now. We'll just focus on that middle graph. So let's see, graph B. Let's add up all the degrees for B. So we have A is degree 2 plus B is degree, this is going to be a little messy, 5, C is degree 3, D is degree 1, 2, 3, 4, E is degree 3, G is degree 3, and F is degree 2. So we add all that up, that's 10 plus 17, so that's 22 total for the degrees of graph B. Now let's count the number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 edges. So that holds true for graph B, and it should for A and C as well. You're welcome to try it yourself. So we'll end here with a couple examples. We've got 4 graphs to look at. So let's see, which one has an Euler circuit, which one has an Euler path, and then we're going to see if the Euler's sum of degrees theorem holds true. So looking at graph A, let's see, do we have a circuit or a path? Well, I don't see any I don't see any vertices that are odd. Everything either has degree 4 or degree 2 in it. So we're going to say that graph A has an Euler circuit. Oops. There we go. And remember, if it has an Euler circuit, it can't have a path, and if it has a path, it can't have a circuit. It's got to have one or the other. Let's look over at B. B has two odd vertices. It's got right here and right here, both with degree 3. Now, if you have two vertices that are odd and no more than 2, then you can have a path. So we're going to say that graph B has an Euler path. Next in graph C, does it have an Euler circuit or a path? This one's going to be neither, because if we look at its odd vertices, we have degree 5 here, another one with degree 5 here, degree 5 here. That's just too many odd vertices. That's not going to work for C. Lastly, looking at graph D, there's a whole lot going on here, but there really are only 2 odd vertices in this entire figure, and that is right here. We have degree 5, and we also have degree 5 going on here. If you look at every other intersection in the picture, it's always an even degree, so something like 4 or 2. So we're going to say that graph D has a path. So no circuit, but a path will exist in graph D, and there are probably multiple paths. Last thing to look at here, does Euler's sum of degrees theorem hold true? Let's look at graph A. So graph A has degrees of, let's see, A. At the top we have degree 2. On the sides we have 4 plus 4 plus 4 plus 4 plus 4 if we're going to count the very center, and plus 2 on the very bottom. So that is going to add up to 24. Okay, so now let's count the number of edges. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 edges. So 12 is half of 24, so that does hold true. Let's look at that for B really quick. B has degree 5 plus, so 1, 2, 3, 4. Sorry, that's not 5 and 5. Let's look at the bottom. 3 plus 3 plus in the very center is 4 plus 4 on each side, and then on the top plus 2. And that's going to come out to be 20. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges in B. Alright, so that holds true for A and B. And I'm just going to go ahead and stop there. You're welcome to try it for C and D, but it should work.